Good morning, everyone. It's a big pleasure to be here and share some of the experiences we had accumulated in the past 3 years developing this device as a service stuff. The idea here is, the idea about this talk is describe some of the opportunities we have applying AI to deliver a device as a service, as well as share some of the challenges and opportunities, case study, and then next steps. Okay, before we move on, I know that the use of AI sometimes is kind of vague, and then I want to clarify. I want to define what I mean when I use AI to deliver a device as a service. And for me, AI is any software dedicated to solve cognitive problems commonly associated to human intelligence. And intelligence is the hard piece here, right? What is intelligence? And then in this case, intelligence is like problems like problem solving, pattern recognition, and so on. Okay? So this is what I'm going to talk. First, a bit of context in terms of HP and AI. I think when we see in the keynote, and it's always difficult to talk with the first after the keynotes, kind of reducing the cheering. It's hard. But in the keynote, I think some of the companies there, and then someone said that less than 1% of the companies apply AI is being successful. And then because most of the problems we have is not having data, and then I'm going to talk about where we get most of our data. And then talk about the opportunities and challenges, speaking about device telemetry. And then in the case study, I'm going to talk about the health management, device health management, which is crucial to a device as a service offering. And then talking about the next steps. Before we move on, here again, when you think about HP is not the same as Hewlett-Packard. If you remember, 2 years ago, we split the company in two different companies, HP Inc., which kept the printing and personal systems business, as well as the new one, 3D printing. And Hewlett-Packard Enterprise kept the enterprise business, storage, servers, networking, and services and software. And here we are talking about HP Inc., responsible for printing and personal systems. And when you see this picture here, although we are saying that we are two leading franchises in printing and personal systems, the challenge here is most of you, when you think about us, you do not connect directly HP with AI, because we build boxes, and most of the devices in this picture here, they seem static, but in the reality they are not. So these devices today are built using smart components. These smart components, they have sensors embedded on them, and then having these sensors, we can get data, we can understand what's the utilization of that specific device, we can understand how the device is being used, why the device is being used, and we can predict the intention of some of the users using these devices. In our perspective today, these devices are more like IoT devices, because we have data, we have sensors, and then we have, they periodically upload this data to our cloud. And then based on this data capture, we are able to propose an entirely different set of services, applying more intelligent services. This is really cool. We need to take care about this privacy stuff, GDPR. We are taking care about this thing. I want to emphasize that device as a service mostly is enterprise. Then we have contracts preventing us to have problems in terms of privacy. When we talk about device telemetry, why we use device telemetry? What are the opportunities here? So having this data coming from these devices, and then I'm talking here about, for example, only 4 PCs, and HP has a long history in device telemetry, especially in the printing side of the business. But I'm a lead data scientist for personal systems, okay? And then if you look only the personal systems, the PCs, we have agents running in about 50 million of devices today. And they are sending periodically data to us. And then based on this, what we can do? So we can propose, we can give back to our designers, for example. They can validate from actual data if the features they include in the new products, they are good or not, if they're being used or not. If the users are engaging in the way they expect the user to engage with the products. This is very important. We can understand the right configurations, the most user configurations that these users are using, our customers. We can understand if they are using certain types of displays, a touch screen, they're using keyboard. But more, I think from the top of the mind, I think the most important here is how do we handle crashes? So this is something very important, especially for device as a service, to understand, to identify the patterns of crashes, to trying to prevent crashes. And when we cannot prevent the crashes, kind of propose a way to overcome the crash. So if, for example, a disk is going to fail, suggest a backup, and then kind of avoid more damage to the users. But in order to have this, we need this data to provide us context. I think someone, again, in the keynote said about the contextualization. So this data brings us context. It's very important because if you look the data randomly, we do nothing about these devices. But if we look at the history of the device, we can have a lot of context. And based on this context, we can propose some insights. Some manual insights sometimes when we are exploring the data, and when we recognize that these insights, they can be automated, we can propose more automatic actionable insights. These are the opportunities, but how we are seeing this, where we are applying device telemetry, what are the areas? Pretty much we can look internally, improving existing products and experiences. And then when I say this, I'm talking about fault detection. So if our devices have the ability to detect the fault, we can kind of propose managers that we can handle crash situations. Another area we are working internally is thermal management, thermal control. Very important, not only for PCs, but for example, if you look at the 3D printing business, a 3D part quality is totally related to manage high temperatures and low temperatures. And if you look, for example, PCs, if we're able to monitor and avoid overheating, we can avoid throttling situations, we can avoid burning in extreme case, or even explosions, as we noticed a couple of years back. So this is very important, that we can look internally and see, okay, we have to do better products, controlling failure and controlling temperatures. Externally, I think the features we are delivering for devices as a service are predictive diagnostics. So our customers, they want to know what's the current health of their fleet. They want to know if they did the right investments in the specific models. They want to know we can also prescribe, look in the data, recipes to optimize the utilization. Then I know that for example, we know the nominal capacity of these devices. But if we know how these devices are being actually used, we can understand, and then we can suggest different configurations. We can suggest different device models to these users. So this is a part of the experience we are doing internally and externally. But I think the focus here are the new experiences. And then when I'm talking about new experiences, I'm talking about natural language and computer vision. And I'm not talking about this because this is hot, deep learning stuff. But I told before that we are thinking these devices as IoT devices. And then if we have these devices communicating with us, and then if we allow the customers to interact using different ways than only dashboards, the experience is much richer. So when we have this ton of data, and then we have a ton of dashboards, it's the same as having nothing. Because if you present to the users only dashboards, IT managers in devices as a service, they cannot see anything because it's too much information. However, if I have a virtual assistant here, and that's the area we are creating virtual assistants. If you have a virtual assistant looking the data and then kind of sending alerts and sending some communication to the IT admins and to the final end customers, it's much richer, the experience. Okay? Speaking about failure detection, when I talk about failure detection, I think, again, in the keynote, someone said that data quality is a big problem. Every time we change a firmware, every time we change the collector, some of the data is kind of, sometimes is generating incorrect information. And then we need to think about, we collect data. This is a post wrote by David Lincoln 4 years ago, and then he was saying, if you want to work with device telemetry, you have to gather information for hundreds, perhaps thousands of devices. Only 4 years later, we are talking about millions of devices, perhaps hundreds of millions of devices. And then it's virtually impossible to see if the data is good or bad. So we need to have automatic outlier detection to see if the data is wrong or bad. And then we have to spend a lot of time producing more quality data proper to submit to our machine learning models. This is 80% of our time or more. Another thing we have to take in consideration is when we are going to create an accurate hardware failure prediction system, we need to think about the imbalancement. Fortunately, less than 1% of the devices, they present failures. So I have millions of devices, and less than 1% of them, they have failures. So most of the time we need to, okay, what are the approach I'm going to use to create models using data, considering this total imbalancement between this good data and the bad data. This is very challenging. And here, I'm coming to the area more practical. What you're seeing on the screen here is the typical approach that we are using today to identify, to classify the health management of a device component. For example, we can use this for disks, we can use this for batteries, we can use this for CPU. But this is typically what we are doing. This is the typical flow. So we have these devices sensing their current state very, very often, and then communicating. Sometimes we have different controllers. We have different data collectors. Then some of them collect data and transmit it to us every minute, some of them every hour, some of them once a day, depending on this. But if you look, for example, data scientists, and then when we are talking about granularity of data to propose a forecast model, they're going to say, no, I need a minute. Then when we look a minute, I need a second. Because some of the systems, they're very nervous in terms of a failure detection. But what we have here is, we have this PCs sending data to our cloud. And then we collect pretty much everything we can. Just give an example in terms of numbers. About 6 months ago, we released a new version of the data collectors. And then we had 60 million devices sending data to us. Okay, and in terms of data, is about 700 gigabytes a day. This is pretty much the volume of data we have here. Only for one of the use cases for predictive maintenance. And then if you look, for example, what kind of the information we have interface errors, if you're looking for disks, surface errors, or reallocated sectors errors. And then what we do here is, we have this raw data. We have to transform this data. We have to filter. We have to rescale. And then we submit it to our machine learning models. And it's amazing that most of the problems we are having today in terms of the multidisciplinarity of the skills of the team. So we have data engineers working together with data scientists working together. So the way we did is we put everyone working together because we're using Databricks. This is very important. This transforms the way we are doing these things. And then our problems pretty much are time series, but more than time series, they are multivariate time series. The challenge there is to identify what features to extract to submit to this time series. And then, okay, we understood that sometimes we use feature engineers, sometimes they're using convolutional neural networks on top of the long short-term memory models, LSTMs, using deep learning. And then we have to transform. If we're using traditional deep learning structures, we have this data, we have everything collected, we have data frames, and then if you want to submit to a TensorFlow model, I have to transform the data frame data to a NumPy array, and then submit this NumPy array to this series, and then train a model. Pretty much, again, stacked LSTMs or sec-to-sec models. And then in the end, we have kind of predictions in range. So we have classes of failures. Failure today, in 30 days, 60 days, more than 60 days. This is pretty much the flow of information we have to implement these predictive diagnostics use cases. In terms of data, I know that this is a very complex diagram, but the most important thing here is we have this data coming from the agents here. And then, again, we treat them as a stream, as an IoT. And then we are using AWS and Databricks as the foundation to our architecture, data architecture. Then we submit this data to Kinesis. Of course, we have identity management using Cognito. And then we kind of group them in some EC2 clusters. And why? It's because the data coming from these devices, they are lots of files, but small files. Then we have to group them, because if you have lots of small files, we cannot have a good throughput. So we group them, create larger files, and then we submit to S3. And there, using Databricks, we start to pre-processing this data. We convert to Parquet, and then we convert this data to a more analytical format. We enrich the data, we understand, we kind of, how can I say that? We transform the data in a different form, in a columnar format. We pivot them, and then we let them ready to 3 different uses. The first one on top, right top, is we have data analysis using Tableau, using data visualization tools, kind of trying to understand and what the data is and to perform data exploration there manually. Then we have the flow in the middle, which are the services that I already know. Disk failure prediction, battery prediction, thermal prediction, resource utilization. So the services that I know, then I can use the data prepared by the Silver data in the middle. So these are the traditional inferencing flow. Then underneath, I have the anomaly detection flow, which is real time, pretty much. So as long as I have the data coming, I have to detect if the data is still in the same distribution than the ones that the models were trained. So this is the 3 objectives I have looking at this picture here. And then having this data, I can show you what you are more interested, which is the machine learning and the training pipeline and the inferencing pipeline. Here, what we use for machine learning pipeline is Databricks for data transformation. So for most of the cases, we have this data coming from telemetry. And then if I want to propose this, submit this data to a model, a machine learning model, and we tried several different machine learning architectures and alternatives. We started using the traditional linear regressions and random forests. They did good, but they did not capture the sensibility of this data. For example, if I have a disk about to fail, it doesn't matter that I have data coming from ears, because a disk starts to present and showing signals of failure less than 60 days from the failure, okay? And then if I apply here a moving average to try to identify what will be the trend of failure, it just not work. So I need to use more sensitive machine learning architectures. And then again, we tried to shift the data, and then we tried to shift the data using multi-layer perceptrons networks. They did good, but not as good. But the ones that really worked are the LSTMs. The LSTMs, in their variations, depending on the use case, they are really working. But using LSTMs is kind of, it's good from the perspective of a solution, but there is a lot of work to do in the data in order to use these LSTMs, right? So I have to filter the data because although we use standardized components, some of the manufacturers, they use slightly variations of the standards, so I need to see the data coming from the different manufacturers. Then I need to, on the fly, identify this and submit this data from one side or another. Normalize, rescale, because even, for example, if I have thresholds for the same variable, for the same metric proposed by the standard, we have some needs to rescale because they vary between the same manufacturer, and then remove the outliers. When I do this, for example, and then look for the right series of data, if I have, for example, if I'm trying to detect failure, I need to have series having failure disks, for example, and series having good disks. And then I reduced from the 45 millions of disks to 100,000 of disks. And then when I look of this, and then I want to train, I have to create windows, label data, and prepare this data into series. When I do this, I have thousands of time series. In terms of scale, I have billions of rows here when I have these devices. And then I have hundreds of thousands of rows to process to submit to a training. And then there is a problem that we are facing. Then I noticed today that Databricks is solving with Horovod. We have to have a distributed training using TensorFlow and Keras. Because, again, the models we have, they take more than a day to train. Every time I submit a new network to train, I have to wait until the next day. And then this is kind of clumsy. And then this is something that we are working. Okay, life is good, I have the training. But the problem here is the inferencing. So I have millions of devices that I need to provide status at least once a day, but pretty much once an hour. And then what is the challenge here is pretty much the same flow, but I need to have this running in a high performance. And again, Databricks is helping us to solve this problem. Because pretty much in the end of last year, we tried different approaches. We tried tensor frames, we tried LFS, and then we tried distributed Keras. And then using distributed Keras, we were able to not only take advantage of the data frames in the Spark, but we speed up the inferencing, the models generating predictions in a scale that before, only, for example, to prepare the data, submit to the model, create the predictions, I spent more than a day to generate the list, submit to the network. And using distributed Keras, I did this 45, 50 million devices in less than a minute using a 4-node cluster. So it's really impressive what we can do in terms of parallel processing for inferencing there. And then with Horovod, I'm looking forward to see the same impact in the training side. These are the typical results we have. So these are the typical outputs we have here. So we have outlier detections using unsupervised anomaly detection. And the reason we're doing this is because most of the times we don't have a ground truth predefined, don't have labels. So we need to combine unsupervised with supervised sometimes to generate this. In the middle, you can see resource user classification. There is peer analytics. And then in the end, we are seeing the multi-class classification using deep learning to classify in different categories. Closing the loop, we have a massive amount of data coming from these sensors in these devices, from the telemetry. Databricks helped us to create clusters in different configurations, different libraries. I think everybody here is suffering the same thing, right? So we need to use different libraries. We need to try. Sometimes they work, sometimes they don't. But if if we using Databricks, this is very easy. My boss sometimes don't like the costs that we create a lot of things and then we have to close these things. But this is something that we are learning how to use these things. And then in the end, the integration with different deep learning models. Again, I think Databricks is taking care of this, but without Databricks, it was virtually impossible to deliver what we are thinking. Next steps. In the technical side, we need to create a more, to bring more software engineering practice to the machine learning creation of these models. It's hard to reproduce when we have more than 2 or 3 data scientists working together in the same set of notebooks. And then also in the data sets. So we are looking for a way to kind of a tight data set with models and then kind of control this, looking forward to ML flow. Improve repeatability. I think everyone has this thing. Sometimes we create a model that has that accuracy, that precision, and then 2 days later, and then we say, can you bring me the data again? Oh, no, let me generate a data set because we changed it and so on. So Databricks Delta, I think, would help us here. And then we need massive parallel processing for training, which Horovod, I think, is addressing. So looking forward to implement these things. In the business side, the increment of the number of AI services, every quarter the pressure is being higher, so we need to deliver faster, we need to deliver more services, and of course improve the user experience. That's it.